My name is Hannah Cisse.
And I'm Joy Grant.
And this is Plankton's battle with global warming. Global warming is definitely one of the biggest issues that need to be addressed. With the advancement of technologies and rising of new methods, carbon dioxide has sincerely increased. Carbon dioxide is one of the most abundant greenhouse gases, meaning as it accumulates in the Earth's atmosphere, it acts as a shield, which holds reflected sunlight, which causes rising temperatures, melting of ice, the disruption of seasons, and many other major impacts. So, the aims of our study is to use calcium carbonate and phytoplankton to reduce this carbon dioxide and heavy metal waste in oceans and seas. Calcium is an important element for growth. So, if we fertilize the regions with calcium, that will increase phytoplankton and reduce carbon dioxide by photosynthesis. The calcium carbonate found in rocks and shells will bind to metals and break down the ions.
So the materials and methods that we used for the phytoplankton was 2 1 liters of seawater, an aerator for oxygen, pipette, microscope, and calcium carbonate. So we created 2 different solutions. 10 grams of calcium carbonate equals to 1,000 parts per million, and 1 gram of calcium carbonate equals to 100 parts per million. And we let them sit over the span of 5 days. The materials and methods that we used for metals was electronic balance, spatula, pipette, test tube, magnetic stir, calcium carbonate, EDTA, which is an acid that binds to ions, and a powder of aluminum, mercury, lead, zinc, and copper. For each metal, we're gonna make 3 samples of each. One will have calcium carbonate, one will have EDTA, and the other will be unmixed. What we're looking for is if the calcium carbonate solution looks like the EDTA solution, then the calcium carbonate did bind to that metal. But if the two come out different, then the calcium carbonate did not bind to that metal. So the results for the phytoplankton was that we noticed that a lot of the calcium carbonate accumulated at the bottom of the container, meaning that the phytoplankton reproduced a lot quicker and faster than the top and bottom. And for the results for the heavy metal waste was that the mercury solution reproduced a clear solution just like the EDTA, meaning that calcium carbonate can bind to mercury. Same with the aluminum, the calcium carbonate in the EDTA solution came out clear, meaning that the calcium carbonate can bind to that solution. For zinc, when added with calcium carbonate, it reproduced a white sediment, meaning that calcium carbonate cannot bind to zinc. When copper was added with calcium carbonate, it reproduced a blue color, but it was a transparent blue, meaning that it can bind to calcium carbonate. And lastly was lead. The lead also reproduced a white sediment, meaning that lead cannot be broken down by calcium carbonate.
So, to conclude, we found out from this project is that calcium carbonate is able to stimulate the growth of marine microorganisms, especially phytoplankton. Calcium carbonate also has the ability to bind to certain heavy metals contamination in seawater, such as mercury, aluminum, copper. However, calcium carbonate is unable to bind with zinc and lead. So, for future references, the remaining of our results will be coming from Winston-Salem State University. Thank you for listening, and this is
Plankton's Battle with Global Warming
by Hannah Cisse and
Joy Grant.
Thank you.
Bye.